now we're going to look at proofs of some of the important theorems in our section. So in our topic today, we had as one of the topics the properties of the matrix exponential, and we saw that there were quite a number of properties of the matrix exponential. One of the properties was that the derivative with respect to time of e to the at was a e to the at. So how does that work? So e to the at is this power series. So I'm going to differentiate that. I can differentiate it term by term. Incidentally, even though this is a matrix quantity, we can still use the basic concept of a derivative. That is, the derivative is, f of x plus delta minus f of x divided by delta. And so we can use that same property here, and we have this relationship. So even though we have matrices, notice that t actually is a scalar variable in all of this, and so we can actually treat it independently. So in this case, it's actually not that complicated. So derivative, so notice that t does not appear there, t appears here, and so when we differentiate, we get this, and so on. As we differentiate, we get all of these expressions. So notice here I have a squared t squared. When I differentiate with respect to time, I'm going to multiply by 2, so that becomes, instead of being 1 over 2 factorial, becomes 1 over 1 factorial. This, when I differentiate with respect to time, I'm going to multiply by 3, so that this becomes 1 over 2 factorial, and so forth. And so the factorial and the t power match. And so now I look at this expression, and I can see that a multiplies every term in this expression. I can factor out a. So here I factor out a on the left, and I get this expression, and this expression is in fact e to the at. I notice, however, that even though I factored out a on the left, I could just as easily have factored it out on the right. There's no reason I couldn't factor it out on the right, in which case I get it in this form. And so this shows that a and e to the at commute as well. So this proves that they commute. It also proves this other property. So the other properties can be proved in a similar manner. Here's another problem. So the statement is that e to the at, e to the a tau is equal to e to the at plus tau. So how does that work? So here's e to the at, it's this power series. Here's e to the a tau, it's this power series. So I use different summation indices just to keep them separate. I can put these two summations under both the same summation sign, and so this is what I get in that case. Okay, so I just combine the two summations, and notice I have summation with respect to k, then the summation with respect to L. There's no reason I couldn't switch them, okay, because these two quantities actually commute with one another. Well, anyway, the summation doesn't matter which order we take the summation. So I combine these two. When I combine these two, I get this expression. Okay, so notice a gets raised to the power k plus L. Okay, because if I have the a multiplied by a power 3 and a multiplied by the power 5, it's just a times a times a times a times a, and so I can combine those exponents in the product of a. T is a scalar, tau is a scalar, so I leave those alone, and so I have this summation. And now I can use what's called the binomial expansion to show that all of this, that this inner sum boils down to this sum. Okay, it boils down. This inner sum actually boils down to this, using what's called the binomial expansion, which is kind of an interesting little thing. So we're left with this expression now is the expression for this. So it's fairly complicated, and we need to pull out some pretty heavy-duty summation theory to be able to pull this off, but it's all very straightforward. So there's a number of properties that are important to us. So in order to prove that the state equation, the way we've listed it, with the exponential times the initial condition plus the convolution integral, to prove that that actually is the solution to the differential equation now, is going to require a bit more muscle, a little bit of effort to do that. So let's take a look. In order to do that, we need an intermediate result, And so I call this a lemma. Others might call it a factoid. And it's this. The derivative with respect to time of this quantity is equal to a times this quantity plus bu of t. Okay, so how do we actually go through and prove this kind of result? So here's the thing that I'm looking for. I'm differentiating with respect to time. Time appears here, time appears here. Okay, so time appears in two places, and so I basically have this quantity multiplied by this quantity, and so I can use the product rule. Whenever you have a derivative of a product, you can use the product rule, which says, you know, if I have product of AB and I'm taking the derivative, I have A prime B plus B plus A prime B plus A B prime. So here's the first one derivative times the second. Then I have the first one times the derivative of the second. Okay, so that's what we have. Now, let's take a look at what's going on. The derivative of e to the at with respect to time is a e to the at. So we already know that property. And then this I just leave alone. And then over here, I'm going to have e to the at times the derivative of this quantity. Okay, so that's the derivative of this quantity. And so using the fundamental theorem of calculus, I get this expression. Okay, the fundamental theorem of calculus is basically the derivative of the integral is equal to the argument inside. Okay, it's the argument inside. And notice that the initial condition actually doesn't come into play here. So it's just the value of, since you're differentiating with respect to time, I just evaluate the thing at the time. And so this is what I get. It's just this evaluated at t. Okay, so that's the fundamental theorem of calculus. And so I notice that e to the at, e to the minus at, that's the identity matrix. Those two are inverses of each other. And so we just get bu. And so notice that this quantity here, I have e to the at outside the integral. I can take that inside the integral. And so I have e to the at, e to the minus a tau, and I have already shown that that's equal to this. Okay, and so I have proven this lemma. Boom. Okay, now we want to prove that this is the solution of the differential equation, the state model. Okay, so it's let's see how this goes. So so if this is x dot then is the derivative of that with respect to time. So I have two terms in the sum, so I can use the summation property of differentiation. And so I differentiate this one, I differentiate this one. Okay, so I just break it up. Notice that the initial condition is not a function of time, so I can take that out of the derivative. And then I have this expression that I can work with. And this expression, I notice I can take the e to the at outside, and I've already actually worked with this quantity. Okay, I took the derivative of this quantity in that lemma that I showed. Okay, the derivative of this with respect to time is a e to the a t minus t naught. Notice that t minus t naught, even though it's offset, I still get the same derivative because I'm actually multiplying the derivative of this with respect to t, and then the derivative of this quantity with respect to t, multiplying it, but the derivative of this quantity with respect to t is just t. It's just 1. So we again use the same properties of differentiation that we have with calculus in general. Even though these are with matrices, they still works. In this case, it's part of the thing that simplifies it is the fact that t is actually just a scalar. And so even though I have these matrices, the matrices actually are made up of the various elements within the matrix, and I'm actually differentiating element by element. And it all comes through in the wash, which is pretty amazing. You can handle things that look this complicated that way. Anyway, so this is what I have. This thing, again, I proved in that lemma, that factoid, and so we plug in what we got there. Okay, we plug in what we got there. So notice I have the bu of t here. So what is this giving us here? A e to the at. So Notice I'm going to factor, I have an a here, I have an a here. I can factor out that a, and when I do, I get all of this stuff, bu of t. But this is exactly what I called x. And so we have x dot is equal to ax plus bu. Whew! Wow. So that was pretty complicated. So I've noticed that I've shown you the result for the linear time invariant case, and it's complicated enough. I will not prove it for the linear time varying case. Okay. We will talk about linear time varying problems from time to time, but mostly we're going to be focusing on the linear time invariant case. So we'll stop here with these proofs. Stay tuned for the practice problems.